Hello, everyone. We're Group 14, and this is our final presentation for Scout, the Smart Cargo Operating Unit with Tethering. And my name is Hardemon-Pace as one of the computer engineers. And we also have Kaylana Brooks as another computer engineer, Sam Orozco as our electrical engineer, and Devani Trent as another electrical engineer. Why Scout? So here's the problem we're solving. Manual material handling causes a ton of workplace injuries, and over 184,000 transport worker injuries were reported in a single year, according to the BLS. And the automated solutions that exist today cost tens of thousands of dollars, and that's way out of reach for most operations. That's the gap we're filling. Scout is a self-navigating cart that follows a designated operator around, cutting down on physical strain and speeding up transport without needing expensive infrastructure or full autonomy. The key features that make that possible are location tracking, load sensing, speed control, and an LCD interface. Goals and objectives. We structured our goals into two tiers. The basic objective is to track the user through UWB-based positioning while avoiding obstacles and maintaining smooth follow behavior. Specifically, that means autonomously following the user's UWB tag at a minimum distance of 1 meter using three anchors with a mounted ultrasonic sensor handling obstacle avoidance. Building on that, our advanced objective introduces closed-loop motor control that adjusts speed based on payload weight with built-in acceleration and deceleration safety limits. This is achieved through load sensing integrated into the fixed bed, which caps motor speed at 1.1 meters per second once payload exceeds 1 pound. And the speed is capped at 0.75 meters per second at maximum payload of 10 pounds. Here we have our engineering requirements. This table outlines the specifications our system is held to. We're using ultra-wideband relative positioning for localization with a following distance of no less than 1 meter to maintain safe separation from the operator. Maximum speed is capped at 1.5 meters per second, and speed limiting is handled through load-based dynamic scaling, adjusting motor speed continuously based on detected payload weight. For safety, obstacle detection uses forward-facing time of flight, an ultrasonic sensor with a range of up to 2 meters, and the system responds to a detected obstacle in under 200 milliseconds. Payload capacity is rated up to 10 pounds, and battery life supports up to 45 minutes of continuous runtime. The three specifications highlighted here, following distance, speed limit method, and payload capacity, are what our final demo is centered around. The component specifications. These are the core components supporting those requirements mentioned in the previous slide. The UWB localization module provides plus or minus 10 centimeters of positioning accuracy, updating at a rate greater than 10 Hz over SPI. The system is powered by a 12.8 volt, 20 amp hour lithium iron phosphate battery pack with a peak discharge rating above 50 amps, supported by a battery management system rated for 40 amps that protects against overcharge, over discharge, and short circuit conditions. The load cell sensor covers a range of 0 to 15 pounds at a zero point 0.1 kilogram resolution, and the motor drive subsystem operates at a nominal 12 volts DC with a peak current of 40 amps and a continuous rating of 20 amps.
Now let's walk through our hardware, how we pick the microcontroller, the UWB localization system, the drive system, and how it all comes together in our schematics. For our microcontroller, we compared three options: the Arduino Mega 2560, the Raspberry Pi 4, and the ESP32. The Mega gave us basic control but no real-time OS support. The Raspberry Pi had plenty of processing power, but only a 20 to 30-second boot time, and the Linux level latency made it a poor fit for real time motor control. So that left us with the ESP32, which has a dual core free RTOS support for real time tasks, built in Wi Fi and Bluetooth. It boots in milliseconds, and it only costs $10, which fit our budget. It also gave us plenty of GPIO pins for all of our peripherals, and the team already had experience with it from coursework. So going into our UWB module, which is used for our localization, we initially selected the DWM-1000 module, which has a 50-meter range, plus or minus 10 centimeters of precision, and low power usage. But when it came time to purchase the module, availability became a problem, and we needed 4 modules, and the DWM-1000 wasn't reliably in stock. So we moved to the DWM-3000, which matches the DWM-1000 on range and precision, and at a plus, uses only about a third of the power and supports more channels. So that availability issue ended up pushing us toward what turned out to be the better part.
For the motor driver, I compared 3 hardware approaches before selecting the DRV8701 with an external MOSFET full H-bridge. The first option was an integrated H-bridge IC where the driver and MOSFETs are built into a single chip. While this simplifies the design, the current capability is limited by the IC's package and thermal performance. The second option was using 2 half-bridge gate drivers and with external MOSFETs, which offers high current capability but requires more components and a more complex control scheme. I selected the DRV8701 because it controls a complete external full H bridge using 4 external CSD19536 KTT MOSFETs. This approach provides the flexibility to choose MOSFETs that meet our current requirements while improving thermal performance through larger copper pores and thermal vias on the PCB. The driver interfaces directly with the ESP32 using PWM and direction signals, making software control straightforward while still allowing forward, reverse, braking, and variable speed control. Overall, this design offered the best balance of performance and scalability for our 12-volt motor control system. This block diagram shows the overall architecture of our electrical system. At the center is the main control PCB, which contains the ESP32 microcontroller. The ESP32 serves as the brain of the robot by processing sensor data and generating the PWM and direction signals used to control the motors. Those control signals are sent to 2 custom motor driver PCBs, one for the left side of the robot and one for the right. Each motor driver PCB uses a DRV8701 gate driver and an external MOSFET full H bridge to independently control 2 12-volt DC motors connected in parallel. This differential drive configuration allows the robot to move forward, reverse, turn, and perform zero radius turns by independently controlling the left and right side. The main PCB also interfaces with the HX711 analog to digital converter for load cell measurements, a CP2102 USB to UART controller for programming and debugging, and 3 UWB anchors that communicate with a wearable UWB tag for localization. Power is supplied by the battery through a fuse for protection, and a buck converter steps the battery voltage down to provide the regulated voltages required by the ESP32 and the rest of the low voltage electronics.
Slide 11, Overall System Schematic. Now I'll be discussing the overall system schematic for S.C.O.U.T. This diagram shows how all the major hardware components are integrated into a single system. The ESP32 serves as the central controller, communicating with the UWB localization modules, the HX711 load cell interface, and the LCD display, plus the motor drivers. Power is supplied from a 12-volt battery through a fused power distribution system, while the sensors and communication hardware operate from regulated low-voltage power. Overall, this schematic illustrates how each subsystem works together to provide autonomous navigation, load sensing, and user feedback. Moving on to the next slide, I'll briefly discuss the power distribution circuit and the UWB module design. As you can see, on the left side is the power distribution circuit, which uses an LM2596 buck converter to provide regulated power for the ESP32 and other low-voltage electronics, while keeping the motor supply separate to reduce electrical noise. On the right is the UWB module schematic. Each module consists of an ESP32 communicating with a DWM-1000 transceiver over SPI, with a dedicated voltage regulator providing a stable 3.3 volt supply for reliable ranging performance. Together, these two circuits provide the stable power and communication required for the rest of the system.
This slide shows the schematic for one of the two custom motor driver PCBs used in our system. At the center of the design is the DRV8701 gate driver, which receives PWM and direction signals from the ESP32 and generates the gate drive signals needed to switch the external MOSFET full H-bridge. Using the external MOSFETs instead of an integrated H-bridge allows this circuit to handle higher motor currents while improving heat dissipation. To monitor motor current, the design includes a 0.01 ohm shunt resistor connected to the DRV8701's current sense inputs. This allows the driver to detect overcurrent conditions and protect the hardware. If excessive current is drawn, the fault in output is connected back to the ESP32, allowing the microcontroller to detect faults such as overcurrent or undervoltage and respond appropriately. Additional support components include the charge pump capacitors, decoupling capacitors, pull-up and pull-down resistors, and a power indicator LED ensure stable operation of the gate driver. Since the left and right motor driver boards are identical, this modular design simplifies both manufacturing and troubleshooting while allowing each side of the robot to be controlled independently.
For the motor control algorithm, we selected PID because it's straightforward to implement and tune on embedded microcontrollers. The tracking error signal from UWB ranging feeds into the PID loop, which outputs motor PWM clamped by our load cell speed limit. The main limitation is that it can overshoot if the gains aren't tuned for payload changes, so we accounted for that during testing. We chose PID for three reasons. It fits a moving target better than path planning would. It's low cost to run alongside our other free RTO tasks, and it's easy to tune in the field during testing. For our programming language, we chose C. It gives us direct access to the ESP32's peripherals, works natively with free RTOs, and adds no interpreter overhead, which matters for real-time control. For our development environment, we chose Platform IO. It integrates with VS Code, manages our library dependencies automatically, and supports both ESP IDF and Arduino frameworks in the same project.
Our software runs in three phases. First, initialization. We verify the motor, UWB anchor, and battery management system connections. Confirm the battery is above 10% and make sure the UWB tag handshake completes before we let anything move. Second is location tracking. This is the main loop where we continuously range against our UWB anchors and feed the tracking error into our PID controller to adjust motor speed and direction in real time. Third is our obstacle detection. A sensor watches for obstacles and either slows the cart down and self-corrects its path or cuts motor power entirely until the path clears. These three phases run continuously as long as the system is powered on. So going into our UWB ranging setup, on the hardware side, our ranging setup uses one tag worn by the user and two ranging anchors, plus one relay anchor mounted on the cart. The relay anchor takes the ranging data from the tag over UWB and forwards it to our main microcontroller using ESP-NOW. On the software side, we built it on the MakerFab's DWM3000 library, and this library was used by the GitHub user KK96 to provide firmware for the UWB module. And it is also worth noting that we initially planned to use trilateration with three anchors, but during implementation, this didn't meet our goals for S.C.O.U.T, and the implementation was outside of the needs for our project. So we had to scale down to two anchors and use one relay anchor. And the limitation to this is that the user needs to stay roughly toward the front side of the cart for reliable tracking.
Slide 18, Main MCU PCB. This slide shows the custom main MCU PCB that I designed for the project. The board is centered around an ESP32S3 Room 1 microcontroller and includes dedicated interfaces for SPI, I2C, and UART communication. These interfaces connect directly to the UWB module, the HX711 load cell amplifier, the LCD display, and the motor driver boards. One of the primary design goals was modularity. each subsystem connected through dedicated headers, making assembly, troubleshooting, and future upgrades much easier while also reducing the wiring complexity. Designing a custom PCB also improved overall reliability by eliminating many of the loose wire connections that are common with breadboard prototypes. Moving on to the next slide, I'll discuss the dedicated power supply board that regulates power for the rest of the system. Slide 19, PSU PCB. This slide shows the custom supply PCB responsible for generating the regulated supply used throughout the system. The LM2596 buck converter and its 39 microhenry inductor efficiently convert the battery voltage into a stable output for the control electronics. During layout, special attention was given to power integrity. High current traces were routed using wide 80 mil copper traces to reduce voltage drop and resistive heating. In addition, multiple vias were placed wherever power changed layers to maintain low impedance current paths. The switching regulator and inductor were also positioned near the edge of the board to minimize switching noise, coupling into nearby analog and communication circuitry. These circuit choices resulted in a compact, efficient, and reliable power subsystem capable of supporting the entire control system. With the PCB design completed, the next step was manufacturing, assembly, and validation of the hardware.
This slide shows the completed PCB layout for our custom motor driver board. The image on the left is the top copper layer, while the image on the right shows the overall board layout after routing. One of the main design goals was to safely deliver the high currents required by the motors while minimizing electrical noise. To accomplish this, I used wide copper traces for the battery input, motor outputs, and high current paths to reduce the voltage drop and improve heat dissipation. The routing was also designed with gradual bends instead of sharp corners to maintain consistent current flow. The board uses a mirrored layout, meaning the left and right motor channels are electrically identical. This simplifies manufacturing, debugging, and future modifications. I also placed the decoupling and bulk capacitors as close as possible to the DRV8701 to provide a stable power supply during switching. Current sensing is implemented using low-value shunt resistors, and screw terminals provide secure connections for the battery, motors, and control signals. Overall, the PCB was designed to provide a compact, modular, and reliable platform for controlling our 12-volt drive motors.
Slide 21. This slide shows the completed printed circuit boards after fabrication and assembly. Once the boards arrived, each PCB was carefully inspected before components were soldered into place, and after assembly, individual subsystems were powered and tested independently before beginning full system integration. This stage testing process made it easier to isolate problems and verify that each board functioned correctly before connecting everything together. Throughout development, we encountered several engineering challenges that required troubleshooting and redesign. One issue involved communicating with the LCD display, which initially produced inconsistent characters and unreliable readings. This was resolved by verifying the I2C communication settings, properly initializing the display in software, and securing all power and communication connections. Another challenge involved the limited number of available connection points as additional hardware was integrated into the system. To solve this, we implemented wire junctions that allowed multiple devices to branch from a single power or single line while maintaining organized and reliable wiring. By systematically identifying and resolving these issues, we significantly improved the reliability of the final prototype and established a solid hardware platform for future development. That concludes my portion of the presentation, and I'll now hand it over to the next presenter.
Lastly, let's cover the administrative side, which includes our budget and our work distribution. So this project is entirely self-funded by the team. Our original target was a budget of $400, but between unexpected problems and additional parts that we needed, that we didn't know that we needed beforehand, especially once we move on to using 4 UWB modules and expanded our PCB count, our total landed us between $770 and $780, so almost $800. We kept our costs down where we could by borrowing parts when possible, but this is an honest reflection of what it actually took to get to a working prototype. So going into our work distribution, on the electrical engineering side, Sam led the main PCB schematic design and layout, plus the HX711 and buck converter schematics, along with the load cell implementation. Devani led the motor driver, PCB and schematic, and motor implementation. On the computer engineering side, Cantrell led the MCU selection and the core software design and implementation. And I myself handled the UWB module selection and PCB design, software design and implementation for that module, as well as our administrative documentation. But all in all, the four of us supported each other across every subsystem since everything on the cart is very interconnected. So that is the Smart Cargo Operating Unit with Tethering, also known as S.C.O.U.T. Thank you for your time.